Okay, now that we've established our governing differential equation, our next step is to solve them. So let's talk about that. As I mentioned in the previous slide, a solution to the governing equation is some spatial distribution of heads that satisfy it. So we are going to look at three different ways to solve the governing equation. First one we'll look at is what we call a graphical solution. It's flow nets. You take a problem domain. This time we're looking at cross sections, and you draw this family of curves, flow lines and equipotential lines that form this net. And so in this case we have water, and there's a sheet pile, and we have soil over here and soil over here, and the water flows down underneath the sheet pile up to the other side. These lines in the direction of flow are called flow lines. These other lines perpendicular to that are contours of head. There are some simple rules we can use to govern how we draw these, and if we follow those rules, then it ends up representing a solution to the governing equation. These were used a lot before computers were as powerful and effective as they are now, but it's still really useful and important to understand how flow nets work. And so we'll spend a day talking about that. Another solution we'll look at is an analytical solution. When you took your differential equations class, you solve for a lot of these. So basically, you define boundary conditions, and you integrate the differential equation, and then you end up solving for a solution. In this case, we get an equation defining how head varies across a spatial domain. For this particular problem, it's flow through a rectangular section of soil. X equals 0 on the left side. It increases to the right. So this equation right here basically defines the shape of this blue line, the phreatic surface in the soil. And then this equation on the right just gives you the total flow rate through the soil. So if we have analytical solutions are great for simple problems. We're going to look at this problem. We'll also look at well equations and flow through an earth dam or levee with a simple trapezoidal cross section, and we'll derive a set of equations that work for either of those. And then finally, we are going to look at numerical solutions. These are the most powerful solutions in that you can apply them to pretty much any geometry. You can solve for anisotropic conditions where kx does not equal ky. You can have multiple materials, and they're really powerful and flexible. And we're going to look at two methods: a finite difference method where we have rows and columns of grid cells, and then we're going to look at the finite element method where we can subdivide the model domain into triangles or rectangular elements. And then basically we satisfy the governing equation over each of these individual elements, and we end up then getting a solution to the overall governing equation. Okay, regardless of which of each of these three techniques we use, we have to define boundary conditions before we can get a solution. So what is a boundary condition? Well, you look at the problem and you look at its boundaries, and you decide what kind of boundaries they are. So for example, here we have an earth dam or a levee with water on the upstream side, and then it's just draining on the right side. So this surface up here on the upstream side, which I'm painting in red, this is a specified head boundary condition, because everywhere along that line the head would be equal to this value. Along the back side down here, this is a seepage face, and basically along this side the head is equal to the elevation. Let's see if I can sketch that here. There's no pressure head, so the head is equal to the elevation. That's a form of a boundary condition. And then here along the here along the bottom, this is a no-flow boundary condition, which I'll call Q equals 0. What that means is the flow is along that line is parallel to the bottom. It doesn't cross through, and so that is a no-flow boundary condition. And then ultimately we are going to solve for a phreatic surface, defining the upper limit of the saturated zone. And this is part of the solution here, so that's not really considered a boundary condition. Okay, so those are the classic boundary conditions we use in this case. Let me exit out of that. All right, now let's look at this case. This is a dewatering exercise. We have some sheet piles driven into some soil, and then there's an excavation made between the two sheet piles, and the water is pumped out. And so if we wanted to calculate, okay, what are the heads going to look like? What are the flow conditions, and then how much water is going to be flowing here? How much water would you have to pump out? So to do this, we would need to define some boundary conditions. So again, this upstream side is a specified head boundary condition. We'll call that H1. The downstream side is a specified head boundary condition. We'll call that H2. And then right here in the middle, that's also a specified head boundary condition. We'll call that H3. And then, let me see if I can get a different drawing tool here. As you go down this side and up the other side, and down this side and up the other side, these are no flow boundary conditions, okay? And then I'll stick with that color there. And assuming we have an impermeable base on the bottom, we're going to have a no flow boundary condition right along the bottom here. Now over on this left side, if you extend it far enough out, you can give it a head boundary condition equal to this height, or just a no flow boundary condition. And typically we just go out far enough, we can consider it a low flow boundary condition, because most of the flow is going to occur right down here, right around the tip of that sheet pile, okay? Now and over here it would come down and up this way. Now something else is kind of interesting about this one is if we were to draw a line right down the center of this problem, I'm trying to do a dashed line here, okay? We could basically split this problem in two and make this middle line here, this could be a no-flow boundary condition. Why is that a no-flow boundary condition? Not because of any physical barrier there. It's because all of the water organically just flows like this. It's symmetric, and so there's some dividing line in the middle where the water just doesn't cross that. So we can treat that as a no-flow boundary condition, and then you could solve either the left-hand or the right-hand side, and that would give you, and then you'd basically flip that solution and duplicate it for the other side, and you're done. So in a lot of cases, for symmetric problems, we only bother dealing with one side. You could create a finite difference or finite element mesh of 1/2 of this problem and solve it. And that would give you just take your resulting flow rate and multiply it by 2, and there's your solution. Or if you could look at the distribution of heads and equipotential lines and copy that and flip it to the other side, and you have a complete solution. So that's actually a really common thing. Okay, now let's look at one last case. In this case, we have it's a cross-section through a farm where we have, this is kind of a free surface here of the water, and we have these drains. These are agricultural drains. It's like a big trench that's been dug down. and then we have irrigation water coming in from the top. So in this case, we have the top here is the water would basically come down and flow like this, flow to the other side, and it goes out this drain. Let's see, one more here. And then on the other side, we get the same thing. The water's percolating down through the vadose zone, and then once it hits here, we get flow like this. It's hard to sketch here freehand. And then we have water coming from the other side. We're going to assume we have similar conditions on the other side. And so we get something like this. Now, once again, if we assume, let me change my color here. Let's try something else. Let's try purple. If we assume a vertical line right through the center of this, we can treat this as a no-flow boundary condition. And down here at the bottom, we have an impermeable base. That's a no-flow boundary condition. And then this right here is a no-flow boundary condition for the same reasons we talked about on the previous slide. It's a line of symmetry. We have equal water coming from the left and the right. Therefore, no water crosses that line. We can treat it as a no-flow boundary condition. Now, what's really fun about this problem is you can imagine if you put a vertical line right through the center, that's another no-flow boundary condition. Water is not going to flow left to right over that because of this line of symmetry. So you could solve this problem either by using this section on the left or this section here on the right, and you would have a complete solution. So again, to solve these problems, before we start, we look at each boundary on it and we mark it as typically it's either a specified head or a specified flow. Something I didn't mention here is we have water coming in the top. That's a specified flow boundary, which is another variant of the no-flow boundary. So we have flow boundaries, we have head boundaries, and once we define those, we are able to solve our governing differential equation.